Google has unveiled a revolutionary quantum chip called Willow, and it's set to redefine the game in two extraordinary ways. But first, let's dive into what makes Willow so unique compared to conventional computers. Whether it's your phone, laptop, or even the world's most powerful supercomputers, they all operate on fundamentally the same principles. Think of it as a super-fast calculator that works with ones and zeros. But here's the twist. Willow operates using the strange principles of quantum physics, the very rules that dictate how atoms behave. Now, here's where it gets fascinating. Many people assume that as computers grow larger or more complex, they're more prone to errors. Kind of like how a longer chain has more points where it might break. But that's not the case here. Quantum computers have always been notoriously difficult to build, but Willow achieves something scientists have been striving for over the past 3 decades. Typically, as computers become larger or more complex, they tend to face more errors, similar to how a bigger house has more things that can go wrong. For regular computers, having more components often means more chances for mistakes. That's just how it's always worked. Until now. Willow turns this idea completely upside down. Instead of becoming more error-prone as it grows, it actually improves at correcting its own mistakes as it gets larger. Think of it like a house that becomes easier to clean the more rooms you add. It sounds almost impossible, but this is exactly what Google has accomplished with Willow. This image highlights one of Willow's most significant breakthroughs. Let me break it down for you. Imagine building increasingly larger teams of workers. These workers represent the qubits, who can catch and correct each other's mistakes. The 3x3 grid, shown in red, is like a small team of workers that can handle fixing one mistake at a time. It's a basic demonstration that the system works. Scaling up to the 5x5 grid brings 49 workers who can manage 2 mistakes simultaneously, proving the system becomes more effective as it grows. Then, there's the 7x7 grid, a much larger team of 97 workers capable of handling 3 mistakes at once. This shows that as the system grows, it becomes more reliable, not less. Here's the revolutionary part. Typically, when you add more qubits, or workers, you introduce more errors. But Willow flips the script. The larger the grid, the better it handles errors. It's like adding more people to a team and reducing mistakes rather than creating more chaos. The yellow connections between the colored squares illustrate how the qubits collaborate to catch and correct errors. It's like a safety net that becomes stronger as it expands. Why is this such a big deal? Imagine having a car that becomes more fuel efficient the bigger it gets. That's not how things usually work. Larger cars typically consume more gas, not less. But with Willow, the opposite happens. Scaling it up actually makes it more efficient and reliable. What's even more exciting is that this isn't just a minor improvement. Researchers demonstrated that Willow retains its quantum properties as it grows. In the quantum world, that's a remarkable achievement. Quantum systems are notoriously fragile, like soap bubbles. Making them larger typically increases the risk of them popping. Yet, with Willow, it becomes more stable as it scales up. That's groundbreaking. What's truly astonishing about all of this is just how quickly it works. Wait until you hear more.
With the random circuit sampling benchmark, the results are pretty surprising. By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications.
One of the biggest concerns many people have is the possibility that this could compromise Bitcoin. However, that's not entirely accurate. When you consider what Bitcoin truly is, it's comparable to a highly secure bank vault with millions of potential combinations. With the technology we have today, it would take current computers centuries to attempt all those combinations. Willow, Google's latest quantum computer, is incredibly powerful, but in a highly specialized way. Think of it as a race car built for a single, unique track. On that track, it's lightning fast, but it can't handle regular roads. To break Bitcoin encryption, you'd need a quantum computer that's more like a Swiss Army knife, one equipped with thousands more qubits than Willow's 105. It would also require significantly higher precision, as Willow currently makes too many errors. Additionally, it would need specialized capabilities that Willow simply doesn't possess. You can think of Willow as a genius puzzle solver, able to tackle intricate challenges in record time. However, breaking Bitcoin security is an entirely different challenge. It's like trying to use a Ferrari to crack open a safe. No matter how fast the Ferrari is, it's not designed for that job. I wanted to address this in the video because I've seen a lot of people claiming that Willow signals the end of Bitcoin. That's just not true. Willow is an incredible machine, but it's not the right tool for this task. One of the most fascinating things I came across recently is something that hasn't been widely discussed. It's truly a mind-bending concept. When Google's Willow quantum computer solves a problem in just 5 minutes, something that would take a traditional supercomputer 10 septillion years to complete, it sparks an intriguing question. How is this even possible? Where is all this computation actually taking place? One explanation, first introduced by physicist David Deutsch, suggests a compelling theory about quantum computers. Quantum computers might actually be tapping into parallel universes to perform their calculations. To understand this concept, let's visualize it. Imagine trying to solve a maze. A regular computer approaches the problem by solving one path at a time, much like a person walking through the maze step by step. In contrast, a quantum computer tackles the maze differently. It explores all possible paths simultaneously, as if multiple copies of itself existed in parallel universes, each trying a different route. Somehow, the correct solution emerges in our universe. This process resembles a massive quantum parallel processing system, where computations seem to take place not just in our universe, but across countless universes simultaneously. It's like having infinite versions of yourself working on the same problem in slightly different ways and combining their answers to find the solution. While this idea is still theoretical and not proven, it helps explain how quantum computers achieve mind-boggling speeds for certain calculations. For instance, they can solve problems that would take longer than the age of the universe with traditional computers, suggesting something truly strange and fascinating is at work behind the scenes. You might be wondering, what's next on the quantum roadmap? Let's break it down. Milestone 1. Beyond classical computing. This stage is all about proving that quantum computers can solve problems that classical computers simply cannot. For instance, Willow has already achieved this by performing calculations that would take traditional supercomputers an astounding 10 septillion years. It's like proving you can build a flying airplane while others are still designing better cars. Milestone 2. Quantum error. Correction. Current quantum computers are highly error-prone. Imagine a car breaking down every few miles. To address this, researchers are working to make qubits, quantum bits, more reliable. Think of it as developing an engine that can self-repair while running. Recently, a breakthrough with Willow demonstrated that adding more qubits can actually reduce errors, much like having multiple backup systems to minimize mistakes. Milestone 3. Building long-lived logical qubits. Right now, qubits have a very short lifespan. The goal here is to make them more stable, akin to creating a battery that lasts for months rather than minutes. Milestone 4. Reliable quantum gates. Quantum gates are the fundamental building blocks of quantum calculations. Without reliable gates, complex quantum programs simply won't work. This step ensures that the calculations can be performed with precision. Milestone 5. Engineering scale-up. Once these foundational pieces are in place, the next challenge is scaling up. This involves moving from creating a single, perfect quantum system to mass-producing thousands of them, much like transitioning from building one prototype engine to manufacturing an entire fleet. Milestone 6. The final quantum computer. This is the ultimate goal. A quantum computer that integrates all the previous milestones into a fully functional system capable of solving real-world problems. Think of it as constructing a fully operational aircraft carrier, as opposed to just a prototype jet. At this stage, we enter the realm of science fiction, superintelligence, advanced AI capabilities, and revolutionary possibilities. The progress in both quantum computing and AI is advancing at an incredible pace, and it's only the beginning. I can't wait to share more updates as Google and others make strides in this field. If you enjoyed this video, I'll see you in the next one.